Welcome to this in-depth walkthrough of the problem titled Find the Count of Good Integers. In this presentation, we will explore the problem's requirements, design an efficient strategy, and walk through a C++ implementation step by step. By the end, we will have a clear understanding of how to handle this advanced combinatorial problem. In this problem, we are given two integers n and k. Our goal is to count how many n-digit integers are considered good. But what defines a good integer? An integer is good if we can rearrange its digits to form a number that meets two criteria. It must be a palindrome, meaning it reads the same forward and backward. Second, it must be divisible by the integer k. For example, if n equals to 3 and k equals to 5, we are looking for all three-digit numbers that can be rearranged into a palindromic number divisible by 5. This makes the problem a unique combination of number theory, combinatorics, and efficient string manipulation. To solve this, we break the problem into four logical steps. Step 1. Generate all palindromic numbers with exactly n digits. We ensure they begin with non-zero digits so they are truly n-digit numbers. For each palindrome, check if it is divisible by k. If not, we discard it. In the third step, for every palindrome that passes the divisibility test, we store a sorted version of its digits. This allows us to identify unique digit patterns that might be rearranged to form it. Finally, for each unique digit pattern, we calculate how many n-digit numbers can be formed with those digits, making sure to exclude those starting with 0. This structured approach helps ensure correctness and efficiency. Generating palindromes directly allows us to skip checking every n-digit number. Instead of brute force, we generate only those numbers that are inherently palindromic. Here's the trick. We only need to build the first half of the number. We then mirror this half to complete the full number. If n is even, we mirror the entire half. If n is odd, we mirror everything except the middle digit to avoid duplication. For example, if n equals to 5 and the first half is 1, 2, 3, we generate 1, 2, 3 to 1 as the palindrome. This method is clean and efficient, ensuring we only create valid palindromes. Once we have a candidate palindrome, we need to determine if it's divisible by k. We convert the palindrome string into a number and check if the result modulo k equals 0. Only those palindromes that satisfy this condition are considered valid for further analysis. To avoid unnecessary repetition, we take advantage of the fact that different palindromic numbers might have the same set of digits, just arranged differently. We sort the digits of each valid palindrome and store them in a set. If we have already processed this sorted pattern, we skip it. This ensures that we only process unique digit combinations, saving computation time. Once we have our unique digit sets, we calculate how many valid numbers we can form from them. This step is say permutations with repetition problem. We calculate the total number of ways to rearrange the digits using factorials. However, two key issues must be handled carefully. Repeated digits. We divide by the factorial of the frequency of each digit to avoid overcounting. Leading zeros. Any permutation starting with 0 is invalid as an n-digit number, so we exclude them. This part blends mathematical precision with practical constraints. Let's begin with the C++ implementation. We start by including the standard headers for strings, vectors, and unordered sets. Inside the solution class, we define our main method, count good integers. We also prepare a vector of factorials computed up to n, which will be crucial for accurate permutations calculation. Inside the method, we initialize a result variable to keep track of the final count. We also use an unordered set to record already processed digit combinations. Depending on whether n is even or odd, we calculate how many digits we need to build for the first half of each palindrome. We then loop through all valid values for the first half of the palindrome. To ensure the result is an n-digit number, we start from the smallest number with the required number of digits, avoiding any leading zeros. We convert the half to a string, reverse it, and then append it to form the full palindrome. If n is odd, we skip the last digit of the reversed half to avoid overlapping digits. After generating the palindrome, we convert it back into an integer and check whether it is divisible by k. If it fails the divisibility check, we move to the next candidate. If it passes, we sort the digits of the palindrome and check if this sorted arrangement has been processed before. If it has, we skip it. Otherwise, we proceed to compute how many n-digit numbers we can build from these digits. To count the permutations, we first create a frequency vector for the digits in the palindrome. This allows us to apply the permutations formula with repeated digits and to consider the impact of leading zeros. Now we compute the total number of valid permutations. We start with the factorial of n, then divide by the factorial of the frequency of each digit to account for reputations. We subtract permutations where the number would start with 0, since those are not valid n-digit integers. This adjustment is crucial for maintaining accuracy. Once we compute the number of valid permutations for this digit combination, we add it to our overall result. After we finish processing all palindromic digit patterns, we return the result as our final answer. Let's go through an example. Suppose n equals to 3 and k equals to 4. We generate all 3-digit palindromes such as 101, 111, 121, and so on. We then filter out those not divisible by 5, like 105 or 115 remain. Next, we look at all the permutations of digits that could produce such palindromes. After excluding those with leading zeros and accounting for repetitions, we arrive at the final count. In this case, the result is 27. Let's summarize the core takeaways. We approached this problem by combining 4 powerful techniques: efficient palindrome generation through mirroring, divisibility checks for each pruning, deduplication using digit sorting and hashing, precise permutation counting using factorials with careful handling of repeated digits and leading zeros. By thinking modularly and applying the right mathematical tools, we achieved a clean and efficient solution.